So today we're scheduled to talk about arrays. I think today is the second. It is. So now arrays also includes this thing called vectors. So we talk about both of those things at the same time. And then there's a couple of other topics coming up. Binary search, where we use arrays and vectors. Sorting, where we use arrays and vectors. These are pretty narrow topics, by the way. Binary search and sorting, very narrow topics. And then application development, that's the last topic in the course. But today we're going to start by talking about arrays. And you'll see here is a list of problems. And most of these problems will all have this format. And I'll give you a function signature, the data type, the return type of the function name, and a list of function arguments. And then your job is to implement that function. And also generally to write test code when it's convenient to do so or possible. And so you'll see there's a long list of functions you need to implement. What I thought I'd do today is look at the sample exams from this exam 3 from last quarter, where I asked questions about arrays and vectors. And we'll just, because I don't give answers to these problems anywhere. So let's go through these and just to get, and as we go through these problems, then I can explain to you what an array is, what a vector is. And then at the same time, you get to become familiar with the kind of exam questions that you'll be asked to solve or answer in the next exam. Once again, this is exam 3, but I've reorganized the course. I only have 2 exams now. So these problems appear on our exam 2. Let's start by talking about what an array is. So I have some sample code here. It just says all tests passed, because we haven't done any tests, so everything is good. Now, an array is a data container. It's a way to contain data. And the container contains data all of the same type. So you may have an array of integers, or an array of string, or an array of double, and so on, or an array of bean jar instances. And let's take a look by looking at the syntax to declare an array of integers. It looks like this. Integer A, 3. There's an array called A, which has 3 slots in it. So this has got, array, we've got 3 positions. The array will look like this, kind of like a 3-dimensional vector. There's the first position, the second position, the third position. Actually, what we do is we number these positions like this. This is position 0, this is position 1, and it's position 2. The size of this array is 3. It's similar to the way we do the for loops. By convention, we start at 0, and we go up to, but don't include a limit. And the number of times we iterate the loop is that limit number of times. So here, the array is of size 3, which is part of the declaration right there. And the array has 3 slots in it, 3 positions. And the positions are labeled with integer numbers, 0, 1, and 2. Now we could also have an array of double. And it's the same thing. We have 3 slots that have labels 0, 1, and 2. Let's go back to int. But now this array, we don't know what's inside the array. We declared it, but we didn't initialize it. So we could print the contents of the array. Maybe we'll use a loop for that. No, we'll start without a loop. Let's do this. Let's print the value at position 0. Now we don't know what it is. We didn't initialize it. I think it'll come up 0. We'll see. It does come up 0. We also have position 1 and 2. Look at that. This is the value in position 1. This is the value in position 2. This is the value in position 3. I'm sorry, position 0, 1, and 2. Count starting at 0. And this is just you can think of this as random data. So we didn't initialize the array. So whatever happened to be in that memory is displayed. So normally we want to initialize the array. So after we create it, we could do something like this. We could say a of 0 equals 15. And say a of 1 and a of 2. Maybe we'll make that 25 and 35. This is how you change the value at a given position in an array. So we assign a value to a slot in an array. We use this syntax. These are these brackets, or braces rather. The braces are brackets. I think they're brackets. We use these brackets. And we put the position label in between the brackets. That identifies a storage location. And we want to assign to that storage location this value, 25 in this case. So it's an assignment operation we're looking at. This is a declaration up here. This statement is a declaration. It's saying, compiler, generate code that will allocate storage to store 3 integers. So that's, if an integer is 4 bytes, that's 12 bytes of storage is set aside right there. And here we initialize the first 4 bytes is set to decimal 15. The next group of 4 bytes is initialized to decimal 25 and so on. So we should be able to print these now. We won't see random numbers at this point. We're in control with that code. There it is. Now there's another way to do this. We can use, if we know what we're going to initialize the array to, we can use an initialization list. So we could do this. Here we're using an alternative syntax. We're not just declaring the array, we're also initializing it. We're defining it. We declare the array, and then we initialize it to these 3 values. There it is. Well, that's convenient. Now, if we try to print what's in A3, we might be able to do that. Or A4. But these positions are undefined. In another language, we would get a runtime error here. But in C++, and it would report, actually, it would report array out of bounds in another language, most other languages. But in C++, just like C, that the array bounds check, it's called bounds checking, is not checked. So the machine code that's generated doesn't check to see whether a supplied index is legal. So we can use illegal indices. There it is, 100, 101, 102, a very big number and a very small number, a negative number. So that's, once again, we're tapping into random memory here and getting random results. So that's a problem with arrays. There's another way to do this. This is an array. We can also, actually arrays are part of the original C language that C++ is based on. And when C++ came along, there were some improvements. Object-oriented design, in other words, classes or user-defined data types were added. And also some data structures were added. And this mechanism called templates, which were used to define the data structures. But they came up with an alternative to arrays called vector. So this data type called vector was added to the language. Now let me show you how to declare that. You do vector, and you have this angle bracket, int, closing angle bracket. Then I give the name of the vector I want, say v. Well, we use a this time, so we don't have to change these. I like to use v for vector, but because we have this test code set up already, I'll use a. And we need to include the header file for that. So it's a vector header file. Now we're declaring a as a vector. And just like the array a, we can initialize a by assigning values to it. And notice I'm not assigning values to a of 3 and a of 4 because we'll get the same result. We'll be able to index those. We won't get an error message saying, array index out of bounds like you would with a newer language. But we will see random data, hopefully. Oh, we get even better than that. We get a segmentation fault. So we're not allowed to index into this memory. The segmentation fault. That means we're trying to access memory that hasn't been assigned to the process. Let's try to access A3. See if we can do that. Segmentation fault. Let's take out that access to A3. Oh, I'm sorry, this isn't right at all. I don't know what I'm doing. This vector A is of size 0, and these operations are not defined. So we could create the vector A of size 3 like that. Sorry, that's probably what the problem is. I'm going to put these back in there. It's a vector of size 3. There we go. Now I get the same as before. So the segmentation fault had to do with trying to assign numbers into these slots that haven't been allocated yet. So, this form of the constructor is used to create a vector with an initial size that's not 0. So without that, the initial size would have been 0. did this. That's a vector A of size 0. Here's a vector A of size 3. Initialize these, and then, but we can look, we can access, the underlying system allocates a block of memory that's a little bigger than we need. And so that block of memory is assigned to the process, so we can index into it without getting the segmentation fault. But when we do, we get some random values. So the fourth item is some big number that we haven't seen, and the fifth item is a 0. There's another way to do this. I'll show you another way. Instead of initializing it like this, we're going to use the pushback function of vector array. So if you look at this, I'm going to say that the size of A is A dot size. Look at this. So I'm going to print A dot size of A equals, and I'm going to call A dot size. I'm going to call the size function on the array, the vector A. And this should print 0. Size of A equals 0. Now, let's add or append or push back onto a value. So the function is pushback. Let's push back the value 900. And now the size of A should be 1. Size of A is 0, and then we print size of A is 1. Size of A is 0. Size of A is 1. And there's our A of 0, by the way. It's showing up. Oops. And let's put this one in here. Size of A is now, this is 0, and then 1, and then 2. And 3. Let's take a look at that. And I'll chop these off. We've seen this already. We understand that we're allowed to index past the end of a vector and an array both, but we won't get an error message about it like we would in another language. So we're going to take that illustration out for now. We're just going to work with 3 values in A. Size of A is 0, size of A is 1, 2, and 3, and then we print the 3 values. Another way to do this is, which is the way that you're going to do this for the assignments. So we'll use assertions. I need to include the assert header, and then let's go ahead and use assertions on that. Instead of printing the size of A is 0, we're going to assert that A dot size is 0. So we don't have to visually inspect it. You know, if there's a problem with our understanding at this point, our assertion will fail. So this is actually easier. And after we do the pushback, the size of A will be 1. Once again, we push back again, the size of A becomes 2. Size of A is 3. And instead of printing this, we're going to use another assertion. We're going to check that A of 0, we're just checking our understanding with assertions. A of 0 should be 900. So instead of printing out the values and visually inspecting them and verifying that they are what we think they are, we're going to use assertions. Now the code will just say all tests passed, all tests passed. Of course, maybe we made a mistake, and maybe our test code is a problem, and I'll make that 701. Then when we run, we'll get a failed assertion. You know, the line with 701 in it. So, oh, what did we do wrong? So this is the style that I'm having you practice in the assignments, to use assertions, to think about assertions. All right, when you can. All right, let's see. Let me show you how to use functions with these. So let's create a function, and we'll call it initialize. We're going to initialize a vector of int. And then we're just going to do, basically, we're just going to, oops. We call the function. We're going to push back these values and then return. Here's our vector A. We call the function initialize, pass in A. And then we want to check to see if the function worked correctly. Anybody see a problem?
With the function?
Yeah, what about it?
It doesn't have the semicolon? I mean, at the end of the brace.
The what?
At the end of the brace, next to the brace, and it's the semicolon. It's not a semicolon.
Ampersand?
Yeah.
Where does it go? Up here?
No.
Well, I'm going to tell you this is the problem with this function. And I haven't talked about this yet. I don't know if people have read ahead or if it's read back or whatever. But the problem is the way we're passing in the parameter v. The function is making a copy of the vector, and we're operating on the copy, and then when we return from the function, we discard the copy, and we never modify A itself. We just modify a copy of A. Let's take a look at that. Segmentation fault. That's because we can't access this here. So that's what's happening. The function is making a copy of the vector v that comes in, and then we operate on the copy and discard the copy. So A is never modified. So we need to tell the compiler not to make a copy. And we use this ampersand here in that position to say, compiler, let v, don't make a copy of the incoming vector. let's operate directly on the data in the calling code. Don't make a copy, operate directly on the object itself. Now when we push back these values, we're modifying A down here. We're modifying the vector that A names. See here, this V, this names the same vector that A names. We all have multiple names, right? One person can have several different ways of naming the person. I'm David. I'm Dr. Turner. 2 different ways of naming me. Just because I have 2 different names doesn't mean I'm 2 different things. I'm just one thing. So now what we're doing with this reference, this ampersand, we're saying let V be another name of the object being passed in as an argument. So now we've got A and we've got V. And it doesn't have to be different. It could be A. This is okay too, but of course we'd have to change it in here. Oops, I don't know why I'm doing that. Something is wrong. We could do it like that. The A down here and the A up there happen to be the same names for the same object, but that's not a requirement. Because these 2 names, A, have different scope. See, this A here is visible from this point down to the end of main. This A here is visible within the body of the function initialize. I'll leave it at V like that. So now let's see this thing run. Alt has passed. We got it now. So this is a topic I said I was going to talk about later. And I talked about it now. So this is called a reference parameter for functions. It wasn't very meaningful when we introduced functions, but now it's meaningful. Okay. Let's take a look. Look, you'll see it here a lot. That's a reference parameter there. See, A is a reference parameter, B is a reference parameter. Is there any questions before I continue, or just? I kind of gave the overview at this point. These vectors have member functions that we access with the dot operator. That's because they're classes. This is a vector class. It's called a template class. So when you see the word vector here, that is a class, but it's parametrized with a data type in here. So we tell the compiler, this is just not an ordinary class. It's a class that's for which the code is based on the kind of data type you want the vector to store. Here we want a vector of integers. We could have a vector of double, or a vector of school bus, or a vector of bean jar. So this is, in fact, a class. And classes have functions that are accessed with a dot operator. So pushback is one. Dot size is another. Those are the 2 main ones that we use. And the other thing about vector is it's got this index operator. So it's a way to access individual values in the vector. You can read the value using this bracket notation is used for reading the value at a position, and for writing or changing the value at a position. Let's use our new knowledge here to solve some of these problems in the last quarter's exam. So here's a function that's called R_identical. So the name of the function, R_identical, and it takes 2 arguments, a vector of int A and a vector of int B, If you read the description down here, it says that check to see that A and B have the same size and that are element-wise identical. So the integer at position 0 in A equals the integer at position 0 in B, and so on. And if they are identical, return true. Otherwise, return false. That's why we have a bool. Function is declared as returning bool, which is short for Boolean. And Boolean means true or false. There was a mathematician named Boole a long time ago who studied, who did research into, I think it was mathematical logic. I'm not sure. And all right, let's implement it. Are identical. The return type is bool. The name of the function are identical. And notice I didn't copy and paste because these, the PDF document has a underlying character set which is incompatible with the compiler I'm using, and I think the compilers that you're using as well. So I didn't copy and paste. If I copied and pasted out of this PDF, I would have strange compilation errors. And I think in this case, the ampersand might have a different internal numeric representation as well as the semicolon. But those would give compiler errors that would be hard to figure out. All right, so are identical. So it's going to be A and B. But that's not exactly what was shown there. Like we have this const keyword. In other words, we want the function to read A. We don't want the function to modify A. So leave A in a constant state as well as B. So B is const, the const parameter. A is a const parameter. So that tells the compiler, don't compile if the code inside this function tries to modify A or B. And I'll show you that. Suppose we did that. The compiler will complain. Watch this. The compiler will not compile this function because we're modifying A. When we said A is const. Let's watch that. Read-only variable is not assignable. A of 0 equals 1. So, oh, that's a read-only variable. If we take const out, we don't have that problem anymore. Well, we get a warning. I better fix that. I'll just return true. I really messed that one up. We need to return true. We got an error because we said we're going to return true or false, but we didn't. So now we're okay. But this is an error. We shouldn't modify the vector. We just wanted the function to see if A and B are equal. We don't want the function modifying A. So I want to make sure that any programmer that ends up using this function in the project doesn't get, A modified. Or the implementer of this function should know that A cannot be modified. So we use const there. Now we get our error message back again. Not a warning, it's an error. So that's no good. All right. So what we'll do here is let's construct two vectors. We'll do vector. So now we have test code. Here's a vector of A. We'll do A dot pushback, say 12. and we'll push back 2. A has size 2. And then we'll have a vector B, and B will be of size 2. A and B are identical. So when we call the function, it should return true, which it does. So when we call are identical with A and B, should return true. So we assert that A and B passed into are identical returns true. Now that's true without doing anything, because our stub returns true. If we had our stub return false, then then we'd have to fix that. All test passed. So the test code is inadequate because we didn't do anything. We didn't do any implementation. So let's try this. Let's take let's declare a vector of int I called C, and let's push back onto C 12 and 2, and we'll test that A and C are identical. So this will work. That's good. But let's do this a little differently. Let's add to C another value. Now A and C are not identical because C has more elements. See, what do we mean by are identical? It means they contain exactly the same elements in the same order. These do not contain exactly the same elements. C has one more. So if we set up the test code like this, then are identical should return false. But it won't, because are identical only returns true. There it is. So I have to fix that. Well, that's pretty easy to fix. If A dot size does not equal B dot size, then return false. A and B. Oh, but wait a minute. This is A and C. Is that a problem? No. There's not any problem at all. These A and B are just scoped to here. They only have meaning inside that context. C only has meaning inside this context here. It's scoped to this area. It's not visible inside the function. So when we call it like this here, this B is getting passed in here as C. B will now be a name that names the same thing that C names here. So B becomes another name for C, the thing that C names. Does everyone get that? That's a conceptual hurdle that some students grasp early in the class, solve earlier in the class, and other students that take a little longer. So I'm just going over that concept extra times so that everybody's on board there. All right, that's called scoping. So now we check that the two vectors coming in, if they have different sizes, we're going to return false. So now this function should work. There we go, all tests passed. And we have another issue here. We really haven't done a full set of tests yet. We need to test a case Think about what case are we missing?
Different order? It's less than.
Not. Yeah, we could test that, but they have. Let's test the case where they have exactly the same number of elements, but the elements differ. So D has got elements 12 and 13. A has got 12 and 2. Now the two vectors are not identical, but they have the same size. So if we call R identical, A with D, it should return false. They're not identical. Now look at what I'm doing here. I create the test that I know is going to fail, right? And then I run it and I watch it fail. That's called a test first development strategy. And that's a very common strategy in industry. All right, you're given a spec, implement R identical. So what do? You write a stub for R identical, and then you write a block of tests, a group of tests that are all fail at the outset. With good test data, test the boundary cases, test all these situations. I'm testing lots of different situations. A situation where they're identical, situations where they're practically identical except one vector has one more element than the other. The other situation where they're the same size, but one element is different. You see, I'm creating different test cases in advance and watching them fail. I'm doing a little implementation as I go along. It's not strict test first development, but it's sort of incremental test first development. And this is common. And go into a job interview, talk about, writing test code first before you implement the system. And your chances of getting the job will shoot up right there at that point, okay? Because it's in vogue right now. And it's considered a healthy approach to writing code. All right, so we have the case here where A and D have the same size, but one element is different in one vector than the other. And so we haven't done all the work we need to do in this function. What we need to do is, after we know that they have the same size, we have to check that the values are pairwise equal. So we start with the index I equaling 0, and we'll go up to A dot size. We could use B dot size, but because A dot size and B dot size must be equal. If they're not, we would have returned false because of that if statement. We know that A dot size and B dot size are equal, so we'll just use A dot size in this expression. Increment I. And so we're looking at each value, for each valid index in A and B. So A of I, I'm going to do this the wrong way. See, as you're learning this, you don't know yet how to think things out, okay? And I'll show you a common mistake that people make. If A of I equals B of I, that's too many I's, then we're going to return true. They must be identical. You see the problem? We're returning true if the first item in A and B are equal, then we're going to return true. You won't even check any other items in the vectors. You just check the first one. So this code will fail. But it's just a common mistake I see. See, we can't, as we scan through the two vectors, we can't check to see that we can't take action if we find a pair that are equal, because they all have to be equal. But if we find a pair that are not equal, we can take action right there on the spot. If A and B are not equal, then we know, oh, that violates our condition that they're pairwise equivalent. We'll return false. After passing through all of the indices for A and B, if we haven't returned false, that means we didn't find any that were not equal. They must all be equal, so we'll return true. Outside of the loop, we return true. Does everyone get that? This is a little intellectual challenge. And I'm going slowly on that. So a lot of you get it right away. Some of you, it just takes a little time to sink in. And this is what I just talked about right now is a common problem that will come up in many problems coming up, not just this or identical function, but in many problems. Actually, it's the same problem with checking for primeness. If we find a divisor, we can return false. The number is not prime. But we have to check every possible value and fail to find a divisor before we return true. So it's the same situation as our algorithm for determining primeness. All right, all tests pass. So there it is. Now on the exam, if I gave you this problem for an assignment, then this is what I would expect you to do. Write these complete test cases with the function implementation. But on this exam, I give you the function signature, so you don't have to write that. You just have to write the implementation. So on the exam, all you would do would be to write this code right there that I've highlighted. I don't need to see the function signature again. Just give me the implementation of the function. I'm not asking for any test code. Just give me those 5 lines. I don't need a main function or anything like that. And some of these, I do ask for test code. Where is it? Here, write test code. Now I want test code. Okay. But that's only one problem I ask for. Generally, I only ask for test code for one problem, usually. Just to make sure that you know how to write the test code. All right, any questions on this problem? Okay. What about this one? Is lucky. Take a minute to read the problem statement. Sorry. All right, so implement a function called isLucky here that takes an integer, a vector of integers, and it determines whether there's at least 1 7 and no 13s. If that's the case, then it's lucky. Return true. But if it's not the case, either it has no 7s in it, or it has a 13 in it, then return false. It's not lucky. And here's some examples. 6 and 4, that's not lucky. 6, 4, and 7, that's lucky because there's a 7. 6, 4, 7, and 13, well, that's unlucky because there's a 13. So let's implement this. So there's some logic there that we have to use. It is lucky. So is this vector v lucky? Once again, I'm going to pair it back to a stub. I'm just going to return true. Here we create a vector, let's use the examples right from the problem. 6 and 4. That's 6 and 4. So if the vector A is got, and I'm going to use vector V. I think V is a better variable to represent a vector. So is V lucky? No. So this should return false. You know, I'm going to use A again. And I'll show you why. That's A. And B. And B was 6, 4, and 7. And then C is the example cases look pretty good. And in the last case, we had a 13. Oh, by the way, this is not lucky, so it's false. This is lucky, that should be true. This is not lucky, that should be false. Now the problem with automated tests, these are called automated tests. We don't use visual inspection other than to see the words all test paths. The problem with automated testing is that you can have bugs in your tests. So if you see a failed test, well, is it because your test code is wrong? Or is it because your target, unit that you're testing is wrong? So, that's one thing, that's one argument against automated tests. I mean, if it's crunch time and everyone seems to be stressed, oh, we got to get this done now, we don't have time to write tests. We're just going to do some quick manual testing, and then we'll let the customers let us know about the bugs after we release the code. Maybe that's okay for a low budget game, right? But for like a banking application, maybe that's not good. Right? So I guess it depends on the context. So anyway, here we go. So this first assertion should fail. And it does. Now we have to find at least one 7. Let's declare a variable 7 found. We'll set it to true or false. We haven't found one yet. And now let's pass through the vector, looking at each element in the vector. And what do? Well, I just went through a whole bunch of iterations in my head, figuring out, do we test for 7 first? Do we test for 13? And I'm bouncing around. I'm like talking slowly, but in my head, I'm thinking about a lot of different cases, right? So I type out the right answer, and it looks, it's not easy. But actually, I'm like just doing all kinds of analysis, which I'm not conveying all that to you. So I make it look artificially simple, I think. And you're the ones that have to figure it out. Right? You'll have to spend a lot more time than me to do these problems. All right. So if v of I, what happens if we find a 13? What do we do? We know right there on the spot, we don't have to look at any more numbers. We don't care if there's a 7 or not a 7. We're unlucky. Or we're not lucky. Just return false right on the spot, right there. We don't have to look any further. And what about if we find a 7? Can we return true right there on the spot? No, because what if happens if the next element is a 13? We can't do that. So, but what we can do is we can make a record by setting our Boolean variable 7 found to true. Remember, we initialized it to false. Now we're going to change its state to true because we found one. But we have to continue in the loop because if we find a 13, we're not lucky. So when we finish the loop, do we just return true?
If 7 found.
Yeah, what happens if we didn't find a 7? We didn't find a 13, but maybe we didn't find a 7. So we got to test for that. That's the whole reason for that variable. So if the 7 is found, then return true. Else return false. You can write it compactly like that, except that word is not. Both of them. Can you believe that? I'm consistently wrong. Ay, ay, ay. Undo. All right. That's putting it all in one line there. But we could break it up. We could do it like this. Watch. Is this easier to read? Is that easier to read? I got another option. Watch this. Just delete this whole thing here. And then just, what happened? There we go. And we'll just return 7 found. How's that? It's less code. Because if we didn't find a 7 and 7 found is false, we're returning false. And if we found a 7 and 7 found is true, we return a true. So that works, right? So what's better, this or that? Or the one-liner? Well, the compiler will not tell us the answer to this. It's this human judgment. Which one do you like? This one?
The last one.
The last one? How many people like this one better than the last? You know, the last one is return 7 found, okay? Or do we write it out like this? How many people like it like this? How many people like it just return 7 found? Really? Wow. You're future programmers. I can see it, really. That's a sign. That is a sure sign. I don't think it's necessarily more readable, personally. I like it the other way, but I think the students who are good programmers would do this. I know that. All right. Let's see if that works. It does. We got it. That's assuming our test code is sufficient. Well, that's another problem. Maybe the test code is not good. Oh, here's one. Let's do this test. Watch this. And I'm not even going to think whether this is true, going to work or not. Let's have a vector of int. Call it D. all right? And it's of size 0. And is it lucky? It has to have at least 1 7, right? It does not have at least 1 7. That's a requirement. There's no 13 in there, but it doesn't have at least 1 7. So I think it's fair to say that that should be not lucky. Without even looking at the code or thinking about it, we see that it works. So that's called a boundary case. We didn't look at the code and analyze it. Are we handling the boundary case? Oh, wait a minute. The boss says, I got a code. I got to write the test first before I even think about the implementation. So let's go ahead and write the test code first. And now it's like, oh, well, why bother looking at the implementation? We just tested that boundary case, so we don't have to analyze our algorithm to see if that boundary case is handled or not. It's a different strategy. Yeah.
What if you have 2 7s and a 13?
If we had 2 7s and a 13, all right, let's do that one. Thank you. That's a good suggestion. That's the way you're supposed to do it. Really push it. So this is E. 2 7s and a 13 will be false, right? See the test code, I don't want to leave a C there. 2 7s and a 13. That should be false, right?
But didn't the script say that if you have 2 7s and 1 13, that should be true?
No, it doesn't say that in here.
I read it wrong.
You should have no, it has at least 1 7. This is like, that's a different condition, right? You're solving a different, and I could have wrote it up like that. Maybe I'll do that on the exam. I'll say 2 7s, and it cancels out, each 7 will cancel out a 13, right? Something like that. So about 3 7s and 4 13s, or 3 7s and 2 13s. Is that lucky? 3 7s and 2 13s? Because each a 7 and takes a 13? Okay. Well, that's all the problem statement. So I think this code is okay. Yeah. Because as soon as we find 113, we declare it false, and we return false in that moment. All right, so coming back to the exam, there's a whole bunch of problems like this. Find the minimum value in a vector v and return that value. That's an int. Write test code to test is lucky. Well, we did that already. Oh, and I want to add one thing about that. Express your test using assertions. And here it says, write test code that tests every statement. So I'm not asking for boundary cases. I'm saying test every statement. That means the test code needs to execute every statement in the function. And that's called coverage. So this is a statement that has to get executed. This return false has to get executed. This statement has to be executed. This statement, all the substatements, each substatement must be executed at least once. Then we say we have good coverage. It still doesn't test the boundary cases, and it doesn't, so it still may not be good code. But on the exam, I wanted you to show me test code that would execute every statement. Yeah.
So would vector B satisfy that?
So vector, say it again?
So would vector B satisfy that task?
No. If vector B by itself, okay? Vector B, look at this. Vector B by itself, this code I have highlighted right here, does not satisfy the coverage condition because that substatement never runs.
But see that, all the 13 in it.
That's in vector B, right? So return false never runs. This runs. That condition evaluates. That runs. Okay, that runs. But we never branch into here. This is a substatement. What I have highlighted there is a substatement of the if statement. That substatement never runs. So B by itself isn't good enough. You have to have at least two vectors. One that has a 7 in it, and one that has a 13 in it. One that has a 13, and one that has no 13 and a 7. I would say at a minimum, you would have it like this. You would have, this would satisfy it on the test, all right? It's not good test code, but you know, it satisfies what I asked for on the test. You know, that would work. Like I said, it's not good test code, but it satisfies the criterion on the test. Even simpler, you could do it like this. Instead of declaring a new vector B, just reuse vector A. We just put a 7 on there. This is better test code, because now it's testing a vector with a 7 and a 13 in it. We'll put a 7 on it, see if the function says it's lucky. Then stick a 13 on it, so now the vector has two values, 7 and 13. Now the function needs to return false. So that's your minimum code for that problem on the test. Oh, let's run it. We gotta run it. There we go. This is like an application problem. Write a program that implements guess the number game. We'll be talking about that later. That won't be in this assignment that we're focusing on now, but we'll get to that later. Count negatives. Look at this. This is an array. It's not a vector. It's an array. We're using those brackets, but it's a two-dimensional array. So this is a topic, we'll have to cover this next time. Two-dimensional arrays. Given a two-dimensional array A with rows, and columns, count and tell me how many negative values are in that two-dimensional array. Return the value as an int. We'll do that next time. Let's remind me to do this next time, if any of you can remember that. And here's search. Search a vector v for a value k. And if you find k in v, return its position. If you don't find k in v, then return -1. We'll do that one next time as well. That's an important one. And then we have binary search, which is a topic for next week. And that's it for this exam. All right, that's it for today. I'll see you later.